Hello and welcome back. So right now we are discussing about precipitation hardening, and in the last lecture we started talking about the mechanism of strengthening in this phenomenon.
Okay, so let us go to the next mechanism of strengthening with regard to precipitation hardening. And this is due to the modulus effect. And again, this is very similar to what we have discussed for solid solution strengthening. This comes because of the fact that the local modulus changes because of a different modulus that the precipitates will have. And due to a different modulus of the precipitates, the energy of the dislocations will also change. And as a result of that, their movement will be hampered. Okay. And the strengthening that you have due to this modulus effect is given by this equation. Okay, last two terms are square root of r and square root of f. So here delta G is the modulus difference, where G is the shear modulus. And rest of the things have their usual meanings. The next mechanism comes from interfacial energy. And the origin of this is the movement of dislocations through the precipitates leading to their shearing. Okay, so let's say dislocation is coming along this path, and then when it encounters this precipitate particle, then it is sheared. Leading to an increase in the surface area. right? When the particle is shared, it creates a step here. At the particle matrix interface, and the magnitude of this step is 1 Burger vector. And this leads to an increase in the surface area, and therefore an increase in the surface energy also. So this increased surface energy has to be supplied in the form of the applied stress. And that is how you have the strength increasing. And if you look at the strength increment delta sigma by this mechanism, it is given as follows. Where gamma S is the surface energy, or to be more specific, you can write particle matrix surface energy. And the other terms we have already defined before. Right, so the entire strengthening here comes from this particle matrix interfacial energy, and that is why the name of the mechanism is given as such. And finally, we have this lattice friction stress. Lattice friction stress is nothing but the stress required to move the dislocations through the lattice. Now the precipitate and the matrix will have different friction stresses, and due to that difference, there will be some hindrance to the movement of dislocations, right? And as a result of that, the strength is going to increase. So the strength increment here, delta sigma, is given as follows. Where sigma p is the particle or precipitate friction stress, and sigma m, of course, the same for the matrix. So it is due to this difference between the friction stresses which gives rise to strengthening when the precipitates form. Alright, so these are the 6 different mechanisms that we have as part of the precipitation hardening phenomenon. Now if you go back to this diagram over here, this particular diagram which depicts the hardness increase with respect to time or the sequence of the precipitation phenomenon, you can see that after the precipitate forms, there is a decrease in the hardness. Okay, so this is because of the fact that the coherency is lost. The theta prime precipitates which formed are coherent with the matrix, and because of that we have seen that coherency strains are generated, and that is what is responsible for the increment in the hardness and the strength. But beyond this, when this equilibrium phase forms, right, then there is no question of any coherency or any maintenance of coherency between the equilibrium phase and the matrix. Right? So since the coherency is lost, there is no coherency strain also, and as a result of that, the hardness will decrease. Okay, so that can be also illustrated with these pictures over here. Right? So when the theta prime forms, or the theta double prime that you had seen, both of these are actually coherent with the matrix, but their lattices are different compared to the parent lattice. Okay, so since the lattice is different, but it is still trying to maintain coherency with the parent matrix, you can see that it is creating some kind of strain around the precipitates, right? So due to this strain, as I said before, the dislocations will find it difficult to move through the precipitates, and as a result of that, the strength will increase. Okay, so these are the coherent precipitates. But when the theta, which is the equilibrium phase, forms, then that coherency is lost. So as you could see, the theta phase is no longer trying to maintain the coherency with the matrix, and as a result of that, there is no lattice strain between the theta phase and the matrix, right? So as a result of that, there is no difficulty for the dislocations to move through this particular phase, and as a result of that, the hardness comes down, as you could see from here, right? After the theta prime phase, when the equilibrium phase theta forms, the hardness also comes down. And if you continue to do the aging beyond this, then apart from the lost coherency, the precipitates will also grow in size, and as you know, the hardness or strength is inversely proportional to the size. As the size becomes bigger and bigger, the hardness will be lower and lower. Okay, so that is another reason why the hardness comes down as you continue to age beyond the peak aging time, right? And that is what is known as the overaging, when the hardness starts to fall down. So to give you a physical picture as to what happens when you go beyond the peak aging time and the precipitates start to grow, what will be the dislocation movement in this case, or how the dislocation movement will change as you go beyond the peak aging time. Okay, so let us try and understand that as to what happens beyond peak aging in terms of the dislocation mechanism. Okay, so let's say we have these two precipitates over here, and there is a particular spacing between them. We will call this interparticle spacing as lambda. Okay, and let's say this dislocation line is moving in this direction. So now at this stage, when the dislocations encounter the precipitate particles, they'll try and move around them by bending through this gap. Okay, so it will try and bow between the particles and bypass them. Okay, and that is how the dislocation motion will be in this case. With a mechanism like that, when the dislocations will bend and bypass the particles by bending in between them. Okay, so in order for that to happen, the dislocation line has to bend, as I said. So as it encounters the particles, the dislocation will try and bend around these precipitates. Something like this. And then for them to actually totally bend and then bypass the particles, this curvature has to increase, right? So as it progresses more, this curvature will increase so that the dislocation can bow around the particles and bypass them. And ultimately, as it bends around, it is going to bypass. But while bending around these particles, what the dislocation line is doing, it is actually leaving a loop around it, like this. And since these two portions of the dislocation in this loop on either side of the particle are of opposite sign, they will annihilate each other, and as a result of that, these loops will be left behind and the dislocation line will continue to move. Okay, so ultimately when the dislocation finally passes through, this will be the scenario. These loops will be left behind and the rest of the dislocation line will continue to move. Okay, so due to these loops, the dislocations which are coming after this, okay, will find it difficult to move through these particles. Okay, so that will contribute to some hardening in this case, but ultimately what is going to happen is, since we are aging this material now for a prolonged period beyond the peak aging time, the distance between the particles will increase because the particles will grow, right? So this lambda is going to increase. So that is the other effect that we are going to see at this particular stage of the precipitation hardening. Particles will grow and lambda will increase. Now what I said before is, for the dislocation to bend around and bypass the particles, it has to make a curvature. So it has to bend with a particular curvature, and the stress required to bend, the dislocation is given by this. If we call that stress as tau, tau will be given as GB by 2R, where G is the shear modulus, B is the Burgers vector of the dislocation, and R is the curvature. And lambda can be taken as equal to 2R. So now if you replace R over here, then you would get tau as GB by lambda, right? And from here, you can easily see that as lambda increases, the stress needed to move the dislocations will decrease, and as a result of that, the hardness and the strength will come down, right? And as I said, at this particular stage of overaging, the particles grow in size, and as a result of that, the distance between them, that is lambda, increases. And as lambda increases, you can see from here, tau, or the stress required to move a dislocation, decreases, and as a result of that, the strength comes down. Okay, so this is the mechanism or the explanation as to why the hardness decreases in the overaging period. Okay, when you go beyond the peak aging time.
So before we finish this lecture, let us take a summary of what we learned today.
Today we basically discussed about the mechanisms of precipitation hardening, and we have also learned that the precipitation occurs in a particular sequence depending on the alloy system. In case of the aluminium copper system, for example, the sequence is like this. It starts from the supersaturated solid solution, then as you age it, GP1 zones will form first, and then the GP2 or the theta double prime forms, and after that the theta precipitate forms, and beyond that, if you overage, then the equilibrium phase theta forms. Okay, so we wanted to understand as to why this hardness increases when the aging is done till the peak aging time. Okay, and we have seen that there are 6 different mechanisms which can operate during this phenomenon, and these are as follows: coherency strain, which is basically the elastic interaction between the precipitate particles and the dislocations; stacking fault energy, which arises due to the different stacking fault energies of the precipitate and the matrix; ordered structure strengthening comes due to the fact that the precipitates can have an ordered structure, and in that case, when the dislocations move through the precipitates, antiphase boundaries will form, and the dislocations will find it difficult to move through the antiphase boundaries, and as a result of that, the strength will increase. Modulus effect arises due to the fact that the modulus of the precipitate and the matrix are different, and as a result of this difference, the energy of the dislocations can change, and that could in turn hinder the motion of dislocations. Interfacial energy comes into picture because at times the dislocations can shear the precipitates, and when that happens, the surface area of the precipitates increases, and the surface energy also increases due to that. And in order to supply that increased energy, the applied stress has to be increased, and that is how you get an increment in the strength due to this particular mechanism known as the interfacial energy mechanism. And the lattice friction stress comes due to the fact that the lattice friction stress, which is the stress required to move a dislocation through the lattice, is different for the precipitate and for the matrix, and due to this difference there is hindrance to the dislocation motion, and it also contributes to the strengthening. So these were the 6 different mechanisms of strengthening that we discussed today. And apart from that, we have also discussed the overaging period as to what happens when you age the material beyond the peak aging time, when you have already got the maximum hardness. If you continue to age beyond that, what will happen? That is also we have discussed. And we have seen that in that case, the dislocations will try and bend around the precipitate particles and try to bypass them. And as they do it, dislocation loops are left behind the particles, and this is a mechanism which is known as OR1 strengthening mechanism or OR1 mechanism. But in this stage, the precipitates also grow in size, and interparticle distance lambda increases, and therefore the stress needed to move the dislocations decreases, because that particular stress is inversely proportional to lambda, and therefore the hardness comes down. Okay.
And with that, we come to the end of this lecture. Thank you for your attention.